Hello everybody, and welcome to our 5.4 concept video. And in this section, now that we know how improper integrals work, we can look at something called probability density functions, which is really how integration, how calculus relates to the world of statistics. So what is a probability density function? Well, a probability density function is an equation that can be used to compute probabilities of quantitative data. And not just any quantitative data, specifically continuous quantitative data. What do I mean by that? Well, good examples of this are stuff that like time is continuous, or distance, anything where you're not restricted to just whole numbers. You can have fractions, you can have decimals, that counts as continuous quantitative data. So a probability density function is something that we can use to actually compute probabilities. The notation we like to use for probability density functions is a capital P. So my function would be capital P of x, where x represents whatever continuous data you're measuring. And probability density functions have three very important properties in order for it to be considered a probability density function. First, the total area under the graph over all the possible values of x, another way to word that is the domain, right, must equal 1. Interesting. Well, let's keep going. I'm going to come back and talk about that one. Second, the height of the graph of the equation must be greater than or equal to 0 for all x values. And this makes sense because this is measuring probability, and probabilities can't be negative. And third, if I find the area under the graph of this density function over a specific interval, that area will represent the probability of observing a value within that range, within that interval range. So interesting. Hopefully, as you guys looked at these properties, you've recognized how this actually relates to calculus. How does it relate? It's because we're talking about area under a graph, which is exactly what a definite integral measures. So if I come back up here and use kind of my calculus notation for this, property number 1 says that the area under the curve, or the definite integral from a to b of my probability density function, must equal 1 as long as my domain is from a to b, right? As long as a to b represents my entire domain. Property 3 just tells us that if you take a definite integral for a specific interval, x1 to x2, this gives you a probability of how likely it is to get a value within this interval, x1 to x2. We actually have a notation for this. We say p of x between x1 and x2. So this is how probability density functions relate to calculus. If I can calculate the integral of the function, the probability density function, then I can find these probabilities. So let's look at some examples of probability density functions, and I want to do that by showing you different types of probability density functions. The first type I want to talk about is what's called a uniform density function. And uniform density functions refer to anything that's completely random, meaning the probability is not changing no matter what value you're looking at. And the reason why this ends up being a probability density function is given a certain domain, a to b, given a finite domain, we can actually find a probability such that the area under the curve is actually equal 1. The area under that horizontal line is equal to 1. Why is the line horizontal? Because the probability is the same no matter what value you're looking at. So this is what a uniform distribution actually looks like. If I pick 2 points within this, take my integral, it's going to find this area, and that area will represent the probability that your outcome is within that range. Another example is what's called an exponential density function. And this one's slightly different because this one, the reason why it's called exponential is because it looks like an exponential decay function that's just starting at your y-axis. So the domain for an exponential decay function is actually 0 to infinity. That's different than my uniform. My uniform, I had to have a finite domain going from a to b. But what's nice about this exponential decay function is once again, with my domain being 0 to infinity, I can actually set up my exponential decay function so that the area under the curve is equal to 1. This type of density function is used very commonly for stuff like wait time. If you're waiting in line, waiting a smaller amount of time is more likely than waiting a really long amount of time. And so we see that decay function there. The third type is what's called a normal density function. And this one's different because this one tails off on both ends, and then I get this little bell shape. And this is one that you maybe have heard about before, right? It's called the standard distribution or the normal distribution. And the reason why this is called normal or standard is because this is commonly used in lots of situations. Because the way this one works is the closer your value is to the average, the more likely it is. And the farther away it is from the average, the less likely it is. This line that it's symmetric around is the average value. We're going to talk more about this one in 5.5, but some things to keep in mind with this one is, what's nice about this one is the domain is from negative infinity to positive infinity, and even though it's got an infinite domain on either side, the area under the curve ends up equaling 1. So it counts as a probability density function. How we actually find that area, that's a question for 5.5. But those are different types of probability density functions, and hopefully as we look to that, you can kind of see a little bit better of how these work. But that's all I'm going to talk about in the concept video, so go ahead and start on the homework, see what you can do, and if you get stuck, check out the examples video. Good luck, and I'll see you in the next one.